All right, so we left last class off kind of looking at the normal distribution, looking at the standard normal tables, kind of looking up different z-values. So we'll kind of pick up from there. Hopefully, all of you go through that Learn Smart, kind of leading us up into this new material. The current Connect assignments up there, probably over fall break, probably like Monday or Tuesday. I'll get that next Excel assignment up there as well. We might just briefly look at it today, so you probably won't even really be able to get started on it too much until next week. I just want to make sure it's up there, so as we start covering material like next Wednesday and Friday, you can start working on that assignment as well. Okay, kind of chipping away at it. So just a reminder, we won't obviously be here Monday because of fall break, so we won't meet until Wednesday next week. Okay. So we left off thinking about these z-values. So what happens if we start out with a variable that's not standard normally distributed? Well, the idea behind what we're going to do, keep it as general as possible, is so we've got some variable x, which we know is normally distributed. We might be interested in finding the probability that this variable x takes on a value somewhere in between two different values. We'll call it a and b for now. We'll work through an actual problem where we put numbers to this, but the idea is we're looking for the probability we're in between two values. Right? We've done this with discrete random variables. We can think about with uniform, we've done this. But with a normal distribution, we've got a few more steps. And the first step is going to be that we have to transform this original normally distributed variable into a standard normally distributed variable. Right? So the way that we're going to do this is we've already kind of talked about, we've got these things called z-scores. Right? So the z-score represented the number of standard deviations away from the mean that a certain x value was. Right? So there is some mean here. We don't know what it is. But we can determine, as long as we know what the standard deviation of this variable is, we can determine how many standard deviations away from the mean these two values a and b are. So once we convert these into z-scores, right? These will be actual values, but for now we're just going to write it in general terms. I can use that standard normal table. When I look up this z-value, it'll give me the area to the left of that, right? And I'm drawing a circle. It's actually the area under the curve, but I'm just kind of drawing a larger circle to make a point. And then I can look up the second z-value, and it'll give me the area to the left of that. Right? Well, if what I wanted was what's in between those two, I could just subtract this smaller area from the larger area, and what I'd be left with is just kind of what's in between those two values. Right? So I can use this idea that standard normal table is giving me the cumulative probability. So if I find the probability it's less than 10 and the probability it's less than 15, subtract the smaller one from the larger, and I'd be left with just what's in between 10 and 15. Right? So that's kind of the general idea behind what we're doing. So we can break this down into steps, right? If I'm looking for the probability in between any two values, first I want to transform those two values into standard normally distributed, a standard normal distribution, or convert them into z-scores. Right? So I'll just subtract the mean, divide by the standard deviation, and that would turn both of these values into z-scores. Once I have those, I can kind of draw this out and think about what region am I looking for, right? And then after I look these probabilities up, right, I'm then going to have a little bit more work to do, because once I have these two probabilities, I have to subtract the smaller one from the larger one. That's kind of what we call like this last step, right? I might use different areas I looked up in the table to find what I actually want. As we work through more examples, we'll see why this is like a little bit, step 4 isn't always the same, right? It kind of depends on what area we're looking for. So let's work through an example where we have some actual values. This is stapled, so. So maybe I've got this normally distributed variable. I think it always helps to just draw this out, also to kind of put some limits on So just let us think about where this probability has to be. So I've got a normally distributed variable with a mean of 5 and a variance of 25. What would my standard deviation be here? Square root of the variance. So I end up with a standard deviation of 5. I want to know what's the probability I see this random variable x take on a value between 10 and 15. So right away, what do I know this probability has to be less than? So if I think about the area to the right of the mean, that should be a probability of 50% or 0.5, right? The mean for a normal distribution is the same as the median, so it exactly splits this distribution in half. If the area under the curve is 1, then the area to either side of the mean would just be 0.5. So if this entire area is 0.5, I'm clearly looking for something that's going to be much smaller than that. So I know this probability has to be less than 0.5, but other than that, I can't really say much. So the first kind of step that I'm going to do is identify the region, but also turn these values into z-scores, right? So I still want the probability in between these two. I could go ahead and use that z-score equation, right, where I'm going to take the value I'm interested in, x. I'm going to subtract the mean, which here is 5, and divide by the standard deviation, which is also 5 here. Now, this gives me a z-score of 1. But even this one was kind of easy given the numbers. I should have been able to know if I remember the interpretation of a z-score. This one would have been a lot easier to find probably without even using the equation. Right? So I think about this. How far away is my value, my x value of 10 from 5? 5 away. If my standard deviation is 5, how many standard deviations away from the mean am I? 1. Now 15 is 10 away from 5. So how many standard deviations away would 15 be? Well, if the standard deviation is 5 and I'm 10 away, I'd be 2 standard deviations, right? So this one was a little bit easier to kind of think about because the numbers were nice and neat about how many standard deviations away I was. I could almost intuitively figure out, oh, 10 is 1 standard deviation away from the mean. 15 is 2 standard deviations away from the mean. Now, when these values get a little bit more, 6.3 and 8.49, obviously we're not going to be able to kind of do that math in our head real quick. And we'll probably have to rely on these equations a little bit more. But ultimately, that's all the equation is doing, right? It's looking at, okay, what's the difference between my x value and the mean? And then to figure out the number of standard deviations that would be, I just divide by whatever my standard deviation is. So once I've turned these into z-scores, I can find the probability I'm to the left, right, of that first z-score 1 by looking up the z-score of 1 in my table. I can then find the probability that I'm less than 2 from that table. If I subtract this smaller area from the larger area, I'd be left with just what's in between these two. So I can go ahead and do that. I'll pull up my standard normal distribution table or my z-table. Where is it? Right here. So I got to rotate it. That's annoying. But I go down, find my z-score of 1.00. So we're looking up these kind of integers, right? 1 is 1.00. So that probability is 0.8413. And then I could look up that z-score of 2.00. That probability is 0.9772, right? I'm kind of trying to complete my drawing over here. This area, 0.8413, 0.9772. Now it's just a matter of subtracting that smaller area from the larger area. Any questions kind of over any part of this process? So, really relying on this standard normal distribution so we don't have to do like the integration of that function between two values. Makes this a lot easier. So we've got that down, right? This is kind of the slide that goes along with what we just did on the board. Right? So I think I've got, oh, and actually, because I know that I want to use this here in a little bit, and because I ran upstairs and forgot to open this, I'll do that right now. But we'll put like a little bit more difficult numbers in here, and also maybe an example that actually has some relevance and not just, you know, kind of a general, you know, we have a you know, a variable that has these values. They don't really mean anything to us. So I mentioned last class that a lot of like different things in biology follow normal distribution. So rainfall happens to be one of those things. So we've got this data of Indiana weather back to what, 1890? No, I think it was 1895. Right. So from this data set, I can find the average monthly rainfall, but also the variance in monthly rainfall. And the thing is that rainfall tends to follow pretty close to a nice and normal distribution. Right. I think, you know, we can break this down by month as well if we wanted to. So I can find June average rainfall and June variance in June rainfall. And even within month, this falls pretty close to normal distribution. Even kind of had the data, I took together a quick histogram. You can kind of see there's a little something weird going on here, but for the most part, right, we get this pretty nice, you know, pretty close to a normal distribution. Right? Nothing's usually perfect, but it's pretty close. The normal will give us a very, very close approximation to these different probabilities. So in 2012, right, there was this really extreme drought. I was also thinking about like, this was a relevant example, and then I realized this has been quite a while now. But I'll bring in some more kind of recent years and some of the examples we'll work through. But this year was particularly dry during the summer in different areas of the state. There were kind of this extreme drought range. And you can even see if we do a timeline, right? So in 2009, kind of February, June, we typically see like a spike in rainfall. This one wasn't that great. You can kind of see in 2010, nice spike in rainfall, 2011. Then we get to 2012, and not only do we not see a spike, it actually kind of like dips down even lower. Right? So kind of not what we expect, kind of out of the convention for kind of the weather patterns in Indiana. And we can actually find out how likely or unlikely it was based off of the historical data that we saw this small amount of rainfall. In fact, I think it was 1.3 inches. So what's the probability that we saw essentially this random variable, which was rainfall, be less than 1.3? Right? That's really what we're trying to find. Okay? So how can we do this? Well, we're going to set up, we know that rainfall is normally distributed. This really is just a matter of converting a normally distributed variable into a standard normal distribution, right? Or kind of convert them into these values of the z-scores. So if I've got my random variable x, which is rainfall, I'm told that it's normally distributed, and the mean is 3.4, and my variance is what, 2.57. So sometimes what I would do ahead of time is determine what that standard deviation is. So if anybody wants to help me out, if I take the square root of 2.57, what's my standard deviation? 1.31. Everybody wants to double check that. 1.603. So we've got a standard deviation that's about 1.6, right? So if we then think about this value of 1.3, the probability of seeing that ranking lower, right? Well, I'm definitely over one standard deviation away from that mean. So I'm starting to get kind of a good distance away. Also, I know that this probability has to be less than what? Yeah, 0.5, because the area to the left of the mean is 0.5. I said last class, any negative z-score is going to have an area that's less than 0.5. Now, the reason why I know this is a negative z-score is because the sign of the z-score tells me what direction of the mean I'm on. If I have a negative z-score, I'd be at a value that's below the mean. For a positive z-score, it would have to be for a value that's above the mean. I can kind of guess what that z-score is. I'm going to just go with 1, but I don't know what the exact value is. These numbers, it's a little bit harder because I've got decimals going on. So I need to convert this into a z value. So how do I do that? Well, I'll take my x value that I'm interested in, 1.3. I'll subtract the mean, which is 3.4. And then I'll divide by the standard deviation, which here, if you didn't find it ahead of time, instead of like plugging in 1.6 or whatever, I could have done the square root of the variance here, right? This would represent my standard deviation. Now that is an actual value. I can go ahead and calculate that ahead of time. But if I wanted to, I can just build it all right into the same form. If I do this, let's see, I probably did. So this is a weird one where the z-score ended up being pretty close to the x value. That does not necessarily have to be the case. It's just the case here because we're dealing with rainfall, which is, a lower range of 0 to 4. As opposed to, I was looking at income, right? Income amounts are never going to be even close to what the z-scores are, right? Because I could see incomes of 40,000, and that might only be 1 or 2 standard deviations away from it, even if it's like 10 or 15,000 away, right? Because the standard deviation on the variable of income is much larger. So once I have the z-score, all I do is go to my table, look up negative 1.3, go over the 0.01 column, right? That's the second decimal, and it'll tell me the probability of seeing that z value or anything below it. So if I do that, we have that in front of them. I look up negative 1.3, what do I get here? 0.0951. Now my fourth step is usually I have to take those probabilities and do some work, but here, the probability the table tells me is exactly what I want. So at that point, I really don't have a fourth step there, right? These are going to be kind of the easier ones because when I want the probability of being less than a certain value, well, that's just a cumulative probability. That's what the table is giving me. Okay. So we go ahead, look this up. Sure enough, we look up in the table, we'll find 0.0951. What if I had asked what's the probability it's greater, we saw greater than 1.3 rainfall? Maybe like a farmer or something. I know that that's like the minimum threshold. So what's the probability that I'll have enough rainfall for whatever crop I've got, and to have enough, I need at least 1.3 inches. What's the only other difference we would do? Yeah, if we wanted the probability of seeing something above 1.3, then whatever value we find from the table, we just have to subtract it. If we draw this out, kind of the visual, I think helps a lot. Any questions on this? All right, so that's the one that we just worked through. So instead, this was actually last September, so this one's pretty relevant. September 2020. We know that within month, the rainfall is pretty normally distributed as well. So let's say we're looking at September rainfall, and we've got the mean of 3.25, the variance of 2.37, and I want to know what's the probability I saw rainfall be as low as 0.47. So once again, we're kind of looking for the probability of being less than a certain value. Should look very similar to the one that we just worked through. So I'll give you guys a couple minutes, kind of work on this, talk to the people around you, work with the people around you, and we'll kind of come back together and see if we can figure out some of the parts that might be difficult on these problems. Let me see. I think this is one. I'll write it up on the board. I think I had an old version. So start working on it. I'll give you some options. So once you work through this one, I choose the answer that's closest to what you come up with. If you actually think through this one, you could probably determine which of these, you could probably rule a lot of these answers out and determine what the answer is with actually going through the entire thing and looking it up. But I want you to get a little practice kind of working through one of these and trying to come up with the exact answers. Here, of the answers I wrote on the board, choose the one that's closest to whatever answer you find. I might be off to the second or third or fourth decimal point. Go for another 30 seconds here. All right, you haven't gotten an answer in, take your best guess here. Thought I counted a few more than 25, so I'm going to close it out. You get everybody in here. All right, I think I counted 29. All right. So, first of all, what should this probability be less than? Which of those answers can you rule out right away? C, D, Y. Think about what we got here. We've got this variable that has a mean of 3.25. Variance is what, 2.83, 2.37? So what's my standard deviation? Approximately, anybody find it? 1.5. So we want to know what's the probability we saw 0.47 inches of rainfall or anything less. So right away, we know the area to the left of the mean is 0.5, so our probability should be quite a bit smaller than that. Right? Now, just because we're like, 3 inches away from the mean, doesn't necessarily mean we're that many standard deviations, right? The standard deviation was 20, being 3 away isn't actually being that far, right? For the standard deviation of 1.5, and if I rough, like I'm grossly rounding here, but I'm close to 3 inches away, which would be approximately 2 standard deviations. Now we're probably not real familiar yet with kind of different z-scores or exactly what makes us kind of have a value that's far from the mean. But anytime we see something more than 2 or 3 standard deviations away from the mean, that's pretty unlikely. Or said differently, right? If I end up with a z-score that's approximately 2, I'm pretty far away from that mean of 0. And the area to the left of my z-score is going to be pretty close to 0, like pretty small. So if I'm guessing over there, I'm probably going to guess A over B. because A is a lot closer to 0 than it is to 0.5. In fact, if I did have something where the probability of seeing that value or anything below it was 0.4, whatever I wrote over there, 0.47, it would have to be a z-score that's just barely below 0, right? Probably something like negative 0.2, maybe negative 0.1, right? We end up with a z-score that's going to be pretty close to, and I put approximately 2 here, approximately negative 2. Right? We're going to be about 2 standard deviations below. So we actually calculate that z-score. What did anyone get off of that? Going back to the step of negative 1.81 should be what that is. How did you come up with that? You just took that value x that you were interested in, 0.47. You subtracted the mean of what? 3.25. And then you divide by your standard deviation, which I asked you for earlier. We'll go ahead and put those values in. We should get about negative 1.81. So I was rounding very inappropriate earlier. So I said it was about negative 2, right? It's a little bit lower, right? Negative 1.81. If I go ahead and look that value up in the table, what's the area to the left of a z-score of negative 1.81? Oh, that was close. Right? So kind of the answer closest to that up there would be 0.0351. Right? I knew it was going to be somewhere around 0.03. Now, knowing right, I have seen this enough that I could kind of recall that from memory. You probably can't yet up to this point, right? So negative 1.81, if we go to this table, the way we look that up is negative 1.8. And then the column that has our 0.01 is this second column. So sure enough, 0.03. Actually, someone lied to me. It is 0.0351, right? Who lied to me? So, right, so this actually is I thought I was actually like, yeah, I thought I remember that, right? So we got 0.0351. That was the area we were looking for, just the area to the left. So we don't really have a fourth step. Okay. Any questions on that one? Okay with this? One thing I want to point out here, because I have had people ask me this. So like, I'm starting to say things like, being 2 or 3 standard deviations away from the mean is very unlikely. So that probability starts to get really small once I start looking at z-scores that are like -2, -2.3. In fact, notice, once I get to like -2.4, the area to the left of that is already less than 1%. I'm at 0.0082 already when I'm just 2.3 standard deviations away. So anytime I go past 2 standard deviations away from the mean or have a z-score of 2 or more, or -2 or less, I guess, right, a larger negative value, my probability starts to get really small. In fact, if we go to 4 standard deviations away, right, -3.9, I don't even have anything out until like the 5th or 6th decimal point. Right, so I'm pretty much at a probability of 0. If I see something 4 standard deviations away from the mean, the likelihood of seeing that, the probability is like less than 0.001%, right? We're getting really, really unlikely events there. So the values in between 0 and 2 are a little bit harder to kind of visualize, but as soon as I get past 2 standard deviations, I should know the probability of seeing something that far away from the mean is really small. Okay. All right, so I already kind of have this drawn up on the board, right? But once we found that probability from the table, that's exactly what we wanted to do. So I had some things in here. I don't know how quickly we'll get through this. I'll probably say this for the end. I think we're gonna jump into Excel for a little bit today, just so we get a glimpse as to how we would do this, not just by hand, but how can we do this in Excel, right? So one of the problems with that table was we can only go to 2 decimals. Another problem with that table, so if I wanted to go to the 3rd decimal, I'd almost need like a 3-dimensional chart and then be able to look up the 3rd decimal on the z-axis. Or I'd actually have to integrate that function myself. I don't want to do that. So I've got this Indiana weather data file. That should be under the in-class data folder on Canvas. So it's not blank. It has kind of all this work in here. I'm going to, actually, this is not the one that you would see. Let me see. I had oh, there's one I didn't save. Let's see if it's this one. I think it is. Yep. Sorry, it should look something like this if you go to that temp-normal sheet. Right. So we have a bunch of worksheets down here. Some of it was like, I think I created the time series graph somewhere on this one. Maybe it was here. Here it is. Yeah, right. Then I've got rain. But we're going to use this temperature one. Right. So not only does rainfall follow a normal distribution, temperature is pretty close to a normal distribution as well. So what I have here is every single month in Indiana for every year, whatever the average temperature was that month. Right? And I think this is a little different in the slides because I think I have, yeah, I've got some newer data here. Okay. So I go up here, and if I wanted to find the overall, right, kind of start labeling this. I'll get out of here. Let's go to view, zoom, so we can see this a little better. Right. So this first row, I calculated the mean, the variance, and the standard deviation. Right. Won't really review that. It's pretty easy, right? All I did was use my average function to find the average temperature in every year, the variance, and I kind of did this a little tricky way. You didn't have to use the annual. You could just select all these. Don't worry too much about that. And then to get the standard deviation, I would just take the square root. But if I wanted to break this down by month, notice I could take the average of the column that has June temperature. That would give me my mean June temperature. Take the variance of that June temperature column. It gives me the variance on June temperature. And then just take the square root of the variance to give me my standard deviation. If I wanted to, I could use that built-in standard deviation function as well. It should give me the same value. Okay. So I did this for 3 different months, right? June, July, and September, right? And I'm actually going to use this value for all of them here, just to give us an idea about what's happening. Okay. So I'm going to delete this real quick and kind of rebuild it for you. So we're going to kind of start off with the same cutoff value. So the first thing that we're going to try to do is find the probability that this June we see an average temperature of 71.4 or lower. Okay. So we know that if we're doing this by hand, we would turn this into a z-score, then look that z-score up on the table, right? And because we wanted the area to the left, that's what the table told us, we'd be done. Right? So we're going to use Excel just to do some math for us first. Okay. It's not going to be a built-in function. We're just going to do math. How do we calculate the z-score? Well, I'm going to take the x value I'm interested in finding the probability of being less than, right? 71.4. Subtract the mean for June temperature, and then divide by the standard deviation of June temperature. Now, if I do this, why is this going to be a problem? I just got a z-score of 43. That doesn't seem quite right, right? I'm looking at a value that's not very far from the mean. So what did I do wrong here? Yeah, right. So a lot of the stuff that we're going to be doing moving forward, we're going to do some of our math in Excel, like, not a built-in function, but just typing in a formula. We have to be really, Excel doesn't recognize order of operations errors because it doesn't know exactly what you want it to do. So we have to be really careful about how we're entering in equations when we're doing math in Excel to make sure that we know that order of operations is working correctly. Right? Often that's just throwing in some parentheses. Okay. So now we're going to find the difference between our cutoff value and the mean, and then we're going to take that difference and divide it by the standard deviation. So that's what we wanted to do. So we end up with a z-score of 0.21, right? So it's only about 0.2 standard deviations away from the mean, okay? Now, if I copy this across, it's going to update everything. So I'll be using the next cutoff value for that month, but it's going to update my mean and my standard deviation to then be looking at July. So if I drag this across here, we start getting different z-scores. And this kind of makes sense, right? If we look at these 3 months, July has the highest. And I think I did September here. Did I do September? This is not September. I have this labeled wrong. This is August. I forgot a month there. So if I look at the average temperature in July, it's the highest in Indiana. So I know that seeing 71.4 in July, well, that's something below the mean, right? In fact, it's quite about 1.5 standard deviations below the mean. So it's going to be less likely I see the average temperature be 71.4 or lower in July than it would be in June, right? And that's because June has a much lower average, right? 71.4 in June would actually be something that's above the average temperature, right? But I can find the probability in each one of these months that I see that average temperature of 71.4. So how can I do that? Well, I've got my z-score. I now use this built-in function called norm.s.dist, right? So what this function does is essentially what we were doing with the table. That's what this function does. It looks up a z-score and it looks like basically looks up in the table for you and then tells you what probability you would have found. Now, what it's actually doing, remember those tables, all those probabilities come from integrating that function from negative infinity up to whatever that z-score is. So really what Excel is doing is it's doing that integration behind the scenes. But if it's easier to think about, it's basically just looking up that z-score in the table for you. Okay? So I tell it the z-score that I want it to look up. And then we're always going to say comma 1 here. So this is cumulative, right? The tables were always giving us cumulative probabilities. So we're always going to put a 1 in there. If you put a 0 in, I don't know. It does some goofy thing in Excel where like, if I didn't make this cumulative, what should the probability of any one value actually be? 0. So what it does is it's not really not making it cumulative. It's looking over like a certain interval based off of the kind of, looking at like an infinitesimally small interval. So, but we're never going to use it. It doesn't really have any practical use for us. So we're always going to put comma 1 here, which means that this function works just like you would looking up the z value in the table. Okay? So sure enough, 0.21, if I were to look that value up myself in the table, so I go down here, if I had a z-score of 0.21, 0.5832, 0.5849. Well, notice this can get a little more exact because it's not constrained to 2 decimals. It didn't have to round the z-score and look up 0.21. It could actually use this value and then integrate the function. So in Excel, we can be a little bit more exact. All right, so that's kind of helpful. Any questions kind of up to this point? All right, so we're just using that, norm.s tells Excel use a standard normal distribution. Then you just tell it your z-score, and then comma 1 to give you the area to the left of that z-score. So, and I could copy this over, right? You can kind of think about the probability that the average temperature in July is 71.4 becomes less likely because, right, now the average temperature in July is a little bit higher, so seeing 71.4 isn't near as likely. And then as the temperature kind of falls back down, the average temperature in August is a little bit lower. Well, now seeing the average temperature of 71.4 lower becomes a little bit more likely. So it's kind of this probabilities, or how we would find those probabilities for the standard normal distribution in Excel. Okay. Any questions on that? So what if I wanted to find the probability of being above a certain z-score? How could I use that norm.s.dist but find the probability of being above a certain z-score? Simply, right? This is where if I've got the area to the left, if I want to be greater than something, I want the area to the right, it would just be 1 minus that. Right? So that would copy that over. Now I've got kind of the probability of seeing an average temperature above that cutoff point for each month. Any questions on that? It shouldn't be too bad. So we have another function that makes life even easier, right? So we've got this norm.dist function. So sometimes we might want to see what that z-score is, right? We might just be interested in how many standard deviations away from the mean that we are. Sometimes we don't care. Ultimately, what we want is just the probability, right? So the norm.dist, what it will do is you tell it the cutoff value you're interested in, x, comma, what is the mean of the variable that you're looking at? So that's up here, comma, the standard deviation of June temperature. And then just like norm.s.dist, comma 1 is the last thing, tells it to make it cumulative. So what this function does is it basically calculates the z-score for you behind the scenes. It has the 3 components it needs to calculate the z-score. So it does that for you behind the scenes, then looks it up in that standard normal table, and returns you the probability of seeing that z-score or anything below it. Now remember, when we're saying things like, what's the probability I see this z-score or anything below it, what we're really saying is, what's the likelihood that I saw a value that was this many standard deviations away from the mean, or anything even further from the mean? So even though we're looking up the z-score, it really relates back to whatever that original value we were interested in was. So here, we don't even have to worry about even thinking about the z-score, because we're just going to put in the value and say, okay, I know that Excel is going to turn this into a z-score and tell me the probability of seeing something that many standard deviations away from the mean or even further. But ultimately, really how I want to translate that, it's the probability of seeing 0.47 inches of rainfall or anything less, or a temperature of 71.4 or anything less than that, right? So we have to use these z-scores as kind of an intermediate step, but ultimately these probabilities speak to whatever that original variable x was. So here, it's going to be the probability that in June, we see average temperature be 71.4 or less, right? So we hit enter here. Sure enough, we get the exact same thing that we found before. And I could copy this over, and I'm getting the exact same probabilities as I did before. I just have a little bit less work. I don't have to calculate the z-score. Excel does it behind the scenes for me. The only issue with this is if I ever want the z-score, well, you know, this function kind of keeps it, doesn't like store it anywhere where I can look at it. Okay. Any questions over anything there? So the first part of that Excel assignment that I'll get up there will kind of look similar to that, where you'll just be given a variable. You'll be told what the mean and the standard deviation is. Or actually, sorry, I probably won't tell you the mean. I will give you the data. You will then calculate using the average and the variance functions in Excel, figure out what the mean and the variance are, and then start to find the probability of seeing, you know, different values, maybe below certain values, above certain values, between two values, right? So if I wanted to find the probability of being between two values, it's just like we did it by hand. I would look up, you know, use that norm.dist to find the probability of being less than, say, 10. Then I would use norm.dist to find the probability of being less than 15 and subtract that smaller probability from the larger one. And that would give me the probability of being in between those two values. So just think of, you can do anything by, you know, in Excel that we were doing by hand. Whereas when you look up those values in the table, now you just have to use that norm.s.dist or norm.dist, depending on if you want to calculate the z-scores or not. Okay. All right, so I'm going to end today with, you know, I told you that these, I don't remember if I showed you this at the end of the last class, right? We kind of talked about the normal distribution pops up a lot, and that's why it's so valuable. So I had some survey data where people responded what their height was. If you graph it out, and I can't remember, I probably excluded one gender here so that I didn't get a fine modal distribution. But right, if I just kind of had one of them, I can graph out height, and it looks pretty close to a normal distribution. I mean, it's a little off here and there, but pretty good, right? Pretty close approximation. I also I didn't show you this before, did I? No. Okay. I also geeked out one day on Instagram, so I saw this. I think this was like this is like a CrossFit thing, so some workout, and I forget what the caption was. I should have said the whole thing was like, are you in the 99th percentile? And it was probably like trying to get people to be excited about how well they did relative to everybody else. But when I saw it, I was just like, this is maybe the coolest, this red, so what is red was women, right? The performance of women at whatever workout this was. I mean, this, I couldn't draw a normal distribution that looks better than this, right? So human performance, when we look at this a lot, really close to a normal distribution. The men was close too, but we had a little bit of a weird thing going on here in this one range. Like we see it pop up all over the place, right? So I had this little data set laying around, and I think this speaks to, you know, it's a normal distribution example, but it also is, I don't know, maybe a good lesson to learn about statistics. So I had this data set, and it was like all these powerlifting meets across the United States, like all these, like every single age was represented. So I kind of cleaned it up, and then I just said, okay, I'll choose one of the lists of these powerlifting meets, which was the deadlift, and I'll kind of look at the distribution. So pretty close to normally distributed for both males and females. There's a little bit of like a longer right tail, but that's pretty easy to describe. because the left tail here, so people who wouldn't have lifted as much, are probably people who like just don't go to compete, right? The people who are going to go compete are probably the ones who are maybe lifting more. So you're always going to have the right side of the distribution a little more overrepresented. If I could like force every single person to compete, well, then I would probably have built out a real nice, a little more of the left side of the distribution, and this would be pretty close to normal distribution. So, you could have this data and someone tells you, well, look, I mean, if I try to find like the average male weight lifted, it's, about 600. Look at females, it's about, 300. So, men are way stronger than women, right? But I mean, this is like asinine, right? So if you look at this data set, you just take a second and think, okay, why might there be such a discrepancy in the mean? I can tell you there was a lot more 400-pound men in that data set than there were 400-pound women. Like there was, so right away you should be thinking about, we've got a very vast difference in the average weight, right? Which someone's weight is probably going to greatly influence how strong or how much they can lift. So I always had this idea that if you could like get two individuals, male, female, who had the exact same height, exact same amount of muscle fibers, there is no biological reason why that male would be any stronger than the female if they had the exact same amount of muscle fibers. So I was like, well, we can at least account for just one of these things, right? I can't account for height in this data set, but I've got every single person's weight. So there's a thing you can do, think about it almost like, I'm going to take the total amount lifted and then just divide it by that person's weight. So now I'm getting this measure of like per pound of body weight, how much does this person lift? So this is something that in the Pagod they call a Wilks score. So this is in the data set. So basically it tries to like factor in the weight of everybody. Now if I graph these two things out, still a really nice normal distribution, which is pretty cool. But if I try to find like the average here, it looks like it's just below 400. I'm trying to find the average here, looks like it's just below 400. I think there was a little bit of a difference in those two, but there's some tests you can run that were kind of outside the scope of this class. And you actually find that statistically, there's no significant difference between the averages of these two, right? So that if you just factor in one thing, which is body weight, there's actually no difference in kind of per pound strength of men and women, right? So I don't know, I thought it was kind of nice because you've got a bunch of normal distributions, but it also kind of highlights that we can't factor in some of these things that might differ between groups. It leads us to wildly incorrect conclusions. Well, if we can start to factor in some of those differences, we can actually get at what the actual answer to the question is. And once we get to like regression, we'll talk about we're actually able to factor in not just one factor, but several factors we can control for. So this is kind of alluding to that. So we will meet again on Wednesday. If you want to over fall break, start working on those homework. Otherwise, try to take it easy, enjoy your time off, and we'll kind of get refreshed and be back at it on Wednesday.